Hello, AP Calc students. Welcome to class. It's 4.2.2 today. And the first topic is, I'm going to give you about 5 minutes and kind of walk around and see where you get. I would like you to write the general area function for each one of those three integrals. In other words, what is a of x? The area under the curve from these left-hand boundaries of 0 to any right-hand boundary of x underneath each one of those three functions. The first one is a straight line at y equals 2. The second one is a upward slanting 5r plus 2. And the third one is a downward slanting 3 over 2 minus k. So the best way to do this would be used to geometry. Start by sketching the region. So make a sketch. You might want to, I wish there was some more room for this. So maybe might be better to do this on a blank section of area, maybe over here. Maybe sketch a quick graph for each one. And then try to determine the general area formula using either triangles or trapezoids or whatever else you can. And see what you come up with. It's important before we go and try to do the 6 problems in 53 that we have the correct answer for 52. So after about 4, 5, 6 minutes or so, we'll check those answers and move on. So that's the first step today. And begin. Start by sketching the graph. I think that's the key component of those three. What's the second one? Is it 4? Is it 4 something plus something? 5r plus 2. Thank you. So that would be 2. Right? I don't want to make it to scale though, because that'll be ridiculous. I'm just making sketches for you. Just to help out with this, because we got to get this done before we do anything else. And the last one is, it's 3 over 2 minus x, right? 1, 2, there's 3 over 2. 1, 2. So the right one, down 1, right there. Is it T? I'm just going to make it X. So for this first one, no matter where that right endpoint is, it's just going to be a height of 2 times the x. So that'd be 2x. Yeah, it's usually number 2. That's kind of it's the trapezoid form is 1/2 times the 2 bases. The left one is always 2. The right one is going to be whatever 5x plus 2 is there times x. And there's a little. Sorry, it's okay. It's all right. You're still looking at these 3 area functions.
No, you're right. It's like you're working with it. Oh.
Looks pretty good, guys.
I think you're alright. Would be funny though.
Well, that's not how it works. Let's try it. So these are ours?
Yes.
Yeah, these are extra. If you want to, that's fine. Oh, hey. This isn't the...
Yes.
What?
Yeah.
So I heard the Casa de your mom. It should be Casa de tu madre anyway.
Yeah, but it just sounds better.
He doesn't fully speak Spanish. He just
That's the
Why?
point.
I know.
I know.
I only know the only one thing you know is tu madre.
The only thing I really know is pendejo, and that's me.
Pendejo.
Yeah, it is.
Sí, yeah, it is. Jeff está en pendejo.
I feel like
Pinche güero.
when you walked in last year to ask Hanky about the fart, because I was in the class.
I can't believe you got him to do that.
The crowning achievement of my
I was-
teaching
I
career
was
too.
looking for that.
I've never done anything more important than that.
And I
Getting
think I said something.
Gwen Hankey to say who farted in Spanish.
Yeah.
I still don't know
But
how
I
you
think
gotta
I
do
said
that.
something to
Just
you,
like-
and you
You
said.
put if you put a camera in front of somebody, this is bad advice, but if you put a camera in somebody and say, "Hey, say it," no, okay.
I think my favorite one was the
That was good too. That was good. Though that turned out really. That was the most fun I've ever had as a teacher because that was like the class. All the seniors were gone, and it was just like me and Beck Berge and Blake Hobson. Like that was it. And we had like 4 weeks of unfettered creativity, and we're like, okay, let's just make a funny video about funny things at school, and that was it. That's what came out of it. Okay. Let's run through some answers really quick because we got to have the answers down in order for the rest of today to make any sort of sense. This is just a review of what we did yesterday. Over here in question A, the area will always just be 2 times x no matter what. The connection, of course, is that if the original function is 2, kind of the function that you would have to take the derivative of to get back would just be 2x. For question B, the area that we're looking for, let's see, I got to think about this one for a minute. If I wanted to do the full trapezoid, it'd be 1/2 times 2 plus whatever 5x plus 2 is, times x. Although, just looking at your guys' work, I suspect some of you are using the antiderivative, which is fine. It's okay.
that seems...
That's what I'm doing in my head to check it anyway. But it would be 5 over 2x squared plus 2x after all that's done. Yeah. And again, that is the thing that if you took the derivative of this, you would get right back up to here, and that's important. And then question C is going to be a little weird. Question C actually has a few different ways to think about it, really. I mean, if you want to do the whole antiderivative thing, you can get the formula really quick. But it really depends on where you put that x. If you put x here, for example, it would be a trapezoid. But if you were to put it right here, it would have to be just a triangle. And then if you put it here, you're going to start having a sum of 2 different triangles, one of which is negative. So this one can get pretty hairy. If I think about it enough, though, let me just kind of play around with this for a little bit. The area of this yellow space, no matter what, that's going to be kind of a constant. As x goes further than that, that's going to be kind of the first place. So I'm going to start with that. That would just be 1.5 times 1.5, half of that. So this would be a of x. This is half of 3 over 2 times 3 over 2. That's the area of the triangle. And then the other triangle, yikes, this might get a little wonky more than I want it to be. I promise it'll shake out to be something nice, though. That little green distance there, that's going to be x minus 1.5, because that's where that intersection is, 1.5. And then the height of this will just be the actual function. That's going to be your 3 over 2 minus x. So the other triangle, this is more work than we have to do for this problem, but be 1/2 times 3 over 2, which is the 1.5, times the, 3 over 2 minus x. That's a lot. It's actually not too rough in the end. Ends up being 9 over 8 plus, I got to think about this for a minute, 1/2 times 9 over 4. Oh, yeah. Minus 3 over 2x. Oh, there it is. 9 over 8 plus 9 over 8 minus 3 over 4x. I feel like I made a mistake in here somewhere. Oh, I'm gonna cut and run on this question. Sorry, guys. As much as you could sit here and stare at me while working through this, let's just talk about the actual answer. It's going to be 3 over 2x minus x squared over 2. And again, that's the thing you're looking for because that will take the derivative. I promise if I had done that algebra problem and shaken it all the way out, maybe if I had practiced a little more ahead of time, I'd have the correct answer, but it's okay. The idea is if I take the derivative of that, I'm going to get right back to the original. This one's interesting because if you build it geometrically, there's a couple of different options on how you want to put that together. But that will do the trick. Anyway, we got to have those 3 written down somewhere right underneath these 3 problems right here because the next thing I'm going to give you is a bunch of other problems to look at. There are 6 of these altogether. I promise you, they're actually relatively simple problems. But first of all, they depend on you having the correct answer for all of the 5 above or all the 3 above problems. This is just 2x. This one was 5 over 2x squared plus 2x. And this one was 3 over 2x minus x squared over 2. Now, the other thing, too, is we're doing kind of a thing where I'm just showing you a formula that you might recognize from yesterday. We did one problem kind of like this from yesterday. Actually, I could probably scroll back up and take a look at it. Just a minute. Hang on. Right here. Perfect. Question C from yesterday. Right there. We had did this whole thing where we kind of geometrically and algebraically proved that b of x, which was the integral from 2 to x, was equal to the a of x minus a of 2. Now, that's actually a really big idea, and we kind of just casually wrote it off real quick of what's going on in that problem. But without showing you the original problem and just showing you formulaically what's going on here, I think what you should notice is that x is going plugged in right there, and 2 is getting plugged in right there. And a of x is just the antiderivative of 4t plus 5. And this is actually sneaking its way into our early discussion of it without really being introduced to anything. This is called the fundamental theorem of calculus.
Wow.
It's part 1 or part 2. There's 2 parts to the fundamental theorem. That's one of them. It's how you evaluate integrals. But before we deal with any of that, you don't need to worry about that right now. I just wanted to point out that I'm kind of giving you that formula today in case you didn't get it. It's right here. I want you to use the formula that, oh no. Oh no, no. That's okay. We didn't lose too much. That happens when I zoom out and zoom in too much on my tablet. I'm starting to figure out what's going on here. Anyway, the formula you got to work with is this guy right here. If you want to evaluate an integral from some constant to some x of f of t dt, what you would do is you would take the area formula for that function and plug in the top bound and plug in the bottom bound and then subtract them. So the first thing you got to do in these problems is connect them back to one of these 3. All 6 of these problems are related to one of these 3 above problems. Like, for example, question A is related to question A. I don't know if you noticed that or not, but they both are something to 2, just 2 dx in there. So a good thing you could do for problem A, just as kind of a push out the door, would just be to use the area function, which is just 2x. And we're going to plug in 8 and then plug in 3 and then subtract them. So this would be 2 times 8 minus 2 times 3, which is going to be 16 minus 6, which is 10. I'll also help you out with B, because when I saw it, I was like, that's just a different problem. But no, it's actually not. I don't know if you remember this or not, but you can factor out constant numbers. So I don't know why you would ever think to write this way, but you could. How about that? You factor out 4. And 4 times 2 is 8. So anyway, I'm going to leave you alone again for a little bit. I'm going to give you about 10, maybe 15. We'll see how long we need. Some time to really think about these 6 problems here. All of them are pretty easy to evaluate. You might want a little more room. I'm probably going to move a couple of them off to the side, but for the most part, you can solve these by, You might have to think a little carefully. Remember, think about the boundaries that you have there. But there you go. Okay. Anyway, we should say 10 minutes and let's see what we get.
Okay, so you all, it's like 4 times 2 times the constant. Yeah, so wouldn't the answer be 56?
I think maybe it'd be helpful for this exercise if I threw the answers down. That would be helpful.
Yes.
Well, just because it would help you know if you've hit the target or not, you know?
May I use the restroom?
Yeah. So this first one is 56. I got 264 for this one.
Yeah, I am.
24. Negative 33. And negative 5. You get 88. I had it all right, so if I did 88 times 3 in my head and got 266, because I don't know how to do the basic math.
So I got 9 to 6 times 3.
Oh.
Do it again. I'll do it again.
Here, I'll show you my work.
I believe you. That's why I'm doing it again.
We did math wrong. Oh wait, we forgot the times it like
What?
silly.
Wait, why is the...
Ah, I
Okay,
got
you're
it.
right.
You're right.
I mean, the first half, not gonna lie.
102.
I put some music on, but I'm afraid it's gonna mess with the recording. So
I don't understand.
What?
It is like
Whoa, what the?
did this, but
for
it's
C?
not. Yeah.
So I plugged in 6 and 2 into the area formula, which was 5 over 2 x squared plus 2 times x.
I forgot that it's area formula and not just the equation.
Go on.
You got 96. No, I got 88.
I wish I had. Oh wait, no, these ones.
Is that a TI
Oh, that's
84
why.
on that here?
Yeah.
Yeah, why?
Isn't it crazy that in 2022 TI still sells the TI 84 for like
What did we do?
And this thing can do the,
No, I got
does those
right, but what did I
the
do?
summations and the interval things like immediately.
$100? I'd ask me.
Can you take that calculator, put that calculator to the...
Okay, so why don't you grab this one?
Oh, just because it was up here, calculator. I didn't want to get mine. Yes, good. Go team.
I don't know.
Oh, wait, no.
64. Yeah, I don't want to do this one. So why don't you have
This one,
2x?
okay, this one is just 2. Yeah, and then the anti-derivative is 2x. A from B.
What did we do?
Nothing, we just went back in time.
Hey.
Dang.
Oh.
Okay. No, we can just do the. So you take the area formula, 5 over 2 x squared plus 2
Yeah,
times x.
I got.
So you plug in the top bound,
44 as well.
6. You plug in the bottom bound,
I
2.
don't know that 45.
Working all the math, do the subtraction. The last thing you do is multiply it all by 3.
I got
I
one.
never got it. Mine, I think.
What did
If
you?
you plug these numbers into 5 over 2x squared.
That's what it was. I was being so silly.
Silly boy. Oh yeah. You could have just looked at that in the top left. We'll bring that guys.
That's what it was. What do you think is an underused word?
Sydney, you're a rock star.
Thank you.
You know what they've done already.
Well, I didn't quite map it out and just. I would have the right thing and just don't want to do the work.
It's understandable. Also a valid strategy. That's one thing I think a lot of times, like College Board, who publishes the test, they like to emphasize like you doing things the long way, I think, for understanding, but then like I don't know, calculator stuff is also really cool. I've been doing with my Algebra 1 classes, I've been like doing more and more like calculator tutorials because I feel like you never have somebody to show you how that thing works. But then like when you learn how to graph a line or whatever and then like find the intersection on your calculator, it's like so much easier than doing most of the other stuff that you can do. 1/2 times base times height plus 1/2 times base times height. Got it. This would be next.
Have you seen the Lego Batman movie?
That's the only Lego movie I haven't seen. I saw the other 3. I think they were pretty good.
Lego Batman movie is amazing, but Sydney, you know how they talk about serendipity in it? You know what I'm talking about? Like where he's like, you complete me, and then he goes, ha 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 ha. And then he's watching Serendipity. I thought that was just a fake movie. It's a real movie.
No, it's a real movie, yeah.
It got 59% on Rotten
Wait,
Tomatoes.
what's the answer? It's PG-13. They're not allowed to.
It's PG-13. And then Robin's like, you have Serendipity? I love that movie.
Serendipity is the movie finale to the television program Firefly.
Not literally, but like. Did you put the answers back up?
Oh yeah, sorry. I was just making sure I could do it, guys. I just wanted to make sure that I could just wanted to flex. That was my 10 minutes. That's kind of yes, sir. Are you vaccinated?
Yes, sure.
I watched those videos all Christmas break, over and over again, just sitting on the couch. Great, good times. There's a whole bunch of them. There's like more than the ones that are on Coney Island. There's a whole bunch. They're all really good.
Well, those are just like the ones that just went crazy, right?
Yeah. I like the one they did outside of Knicks game. Like the Knicks won a basketball game, a bunch of fans just going bonkers. Bill Wirtz,
Yeah, my
His-
favorite YouTuber ever.
History of the World.
Yes.
I remember when he was on Vine, and then he was like, I want to make longer videos. And then he made those two. He dropped those, the History of Japan and History of the World, and then dipped.
At the airport terminal.
No.
Or Mouse at Holland's about to blow up. Those are phenomenal.
Okay. Those Bill Wirtz?
Yes.
Let me just kind of take a pace around the room and see where you guys are on these ones. If you're good, we're good.
That confused the crap out of me.
Which one?
What he said when he was describing, they were saying the description of that.
Well, you gotta watch the TV show first. You gotta watch Firefly. Yeah, Serendipity is the wrapping up because there's a TV show called Firefly, which was very beloved by fans. It never really found an audience. They only made 13 episodes of it. And then like 5 years later, they finally found the funding. They're like gonna make a movie, so they have to wrap up the story. So I highly recommend it. If you're a fan of sci-fi, it's very, very good. Which you're reading Dune, so that's already a good.
This movie doesn't seem like a sci-fi movie.
Serendipity?
Uh-huh.
Maybe I'm thinking of I'm thinking of Serenity. I apologize. I withdraw everything I just said. Serendipity has nothing to do with the movie Firefly. I apologize.
This is what it's on a magical night when they're in their 20s. Jonathan meets Sarah. He finds in love at first sight, but Sarah.
I apologize for anybody watching this video after the fact. This is irrelevant. Please skip ahead 2 minutes.
3,000 miles between them must decide if fate wants them to be together again. When love feels like magic, it's called destiny. When destiny has a sense of humor, it's
Serendipity. There it is. That's your tag. All right. We could talk about a couple of these. I guess the only notes I really have walking away from these problems, on question D, what you want to do, I'll get rid of 24 for a minute, but what you guys probably figured out is that this is just one integral, 1 to 3 of 5x plus 2. A lot of times you can use your integral rules to make things look a little better. You can combine those together. Question F, you might have noticed, is backwards. You have a 0 on the bottom and -2 on the top. So what you want to do is make this the negative integral of -2 to 0 of 3 over 2 minus k dk. And then from there, you would use the antiderivative, plug in 0, plug in -2, and subtract to get -5. Again, the answers are there. So at this point, if you wanted to, you could keep working on these and think about them a little more, especially if you're watching this video again after the fact. But let's talk about this math notes box for a minute, because as we go forward into the class, the math notes are a thing we'd want to make sure we actually take a minute to sit and ponder before we go on, because a lot of times these are going to be information dumps of stuff we need to know going forward. Things where the explorations that we do in class get kind of formalized into like, these are the rules, here they are. So what we've been dealing with so far are what are called definite integrals. And there is such a thing coming up for you as an indefinite integral, but for now, definite integrals are where we're going to be. A definite integral just has boundaries on it. Like you'll see an a and an x, or an a and a b. That's it. And here it is in print for the first time here, but this type of definite integral results in a function called an antiderivative, which is often noted with an uppercase letter, which we have seen before. So, in other words, here it is in formal writing, in case you haven't thought about it too much. The integral from some constant a to a variable x of f of t dt is going to be equal to the antiderivative of x. There are some interesting language things happening here. I don't know if you're noticing or following along with what's going on, but first of all, it's not f of x, it's f of t dt, and that's that dummy variable that we talked about a little bit the last couple days. Dummy variable. And the reason is because the variable we're concerned with in this function is actually x. And x is the right boundary of what's going on here. So what we're doing is, by using f of t dt, we're locking some function in place. And the thing we're concerned about is what's going to happen as we move that right bound underneath that curve. That's what's happening. Some more things to be aware of here. The antiderivative f of x, shown above, can be interpreted as an area function, which is one of those CPM things, one of those teaching things that we're going to be using as kind of training wheels before we actually formally define it. For now, you can think about the antiderivative as the area function, which is what we've been doing. And it will determine the area under the graph of y equals f of t from a to any value of x. What we're going to eventually go to later on is we're going to think about the capital F of x as what's called an accumulation function, which is useful for not just areas, but all sorts of functions that involve rates of change. And you'll see these questions all over your AP test, lots of story problems coming your way. A lot of popular questions involving snowfall. Snow is falling at a certain rate and being removed at a certain rate and comparing how much snow there actually is. You can use integrals to measure all that stuff too. So we're going to stop thinking about them as areas and start thinking of them as accumulations. The same way that distance is actually an accumulation of many different velocities over time, which we have thought about sometimes. If you were to take the speedometer reading of your car over every second for 60 seconds in a row, you could add it up and figure out how far you had actually gone. That's an accumulation function. The other thing to be aware of here, we've talked about it a lot, and it's not going anywhere. A few of you missed it on the last quiz we did too, but whenever you do a general antiderivative, you got to have a plus c on there. One thing we saw yesterday is that changing the lower bound will change the antiderivative by a constant, which is why every antiderivative has a lot of different variations, and they come in the form of the same thing, but plus some sort of constant. That doesn't matter when you take the derivative because they go away, but you have to remember that when you do an antiderivative, you have to put a plus c on there, which is a thing that we'll see over and over again. You can find many memes on TikTok from fellow calculus students about the same thing. It's a popular joke every year. I've avoided those kind of hack jokes. I don't do plus c jokes, but you know.
Well, you should.
It does get the likes though. When you do the hacky jokes.
Joke right
I don't know. I'll look up some good ones. I have a Google Doc going with some plus c's. There's one where it's like it's the three kids from Harry Potter. It's Harry, Ron, and Hermione, and it's college board is Professor McGonagall, and she says, when something's going wrong, why is it always you three? And I think Harry is plus and minus, like positive negatives. Ron is plus c, and Hermione is the calculators not in radians. That's what it is. That's the joke. Haha, hilarious. Let's talk about a couple other quick problems before we finish up today, and then you'll have some time to work on the homework assignment, which is kind of a longer one. So I'll give you some time, but this will be a good chance to summarize everything here too. Peter, what's up?
Get out of here, Mike.
Problem 453. We have a millipede moving along the edge of a centimeter ruler with a velocity v given by this function. Velocity is 3t minus 9, and it's measured in centimeters per second. I don't know. I think you know, it could be anything. These questions are really popular on AP. I don't know why. It's either a bug moving along a line or it's a particle moving along the x-axis. But
At least they're not spiders.
that's true. It could be anything. What we're going to do here is in question A, we're going to write and evaluate a definite integral that can be used to calculate the displacement of the millipede over the interval t equals 3 to t equals 6. The more you read these problems, the more you realize that the integral notation is actually very useful here because it's basically already written for you. In fact, all we need to do is the integral from 3 to 6 of our velocity function, v of t dt. A very powerful thing to be understanding right now is that English sentence translates itself into those mathematical symbols really easily, which is a really cool thing. So the displacement of the millipede over the interval from 3 to 6, interval from 3 to 6, of your function, v of t dt. We're also going to evaluate this, so let's go. Right now, again, we don't really have any tools for this other than the vague formula that's starting to form right now, but also we can do geometry. This would be the integral from 3 to 6 of 3t minus 9 dt. Yes. What? What are you talking about? 3 to 6. 3 on the bottom, 6 on top.
Yeah.
Yeah, bottom,
So
top.
this is the right
And then, I think he's thinking like when you find it, it goes.
Oh, yes. If I was going to do that formula, which I'm not going to do here, but, well, I am going to in part B anyway, but let's draw a picture of this really quick. Let's make a quick sketch of a graph. What's interesting, actually, I'm going to move my x-axis up here because this is the graph of 3t minus 9. And we're interested in 3 to 6, which, if you know what's going on in this particular function, at 3 there's going to be a 0. 3 times 3 minus 9 is 0. And then from there it's got a slope of 3, so it's going to be going up from there. So this graph kind of looks like this. And as far as, let's see, 4, 5, and 6, as far as the answer for this first problem goes, we're going for the area under the curve from 3 to 6. It's just going to be a triangle, so we could easily find it by using the triangle formula. So for part A of this problem, that integral there, the integral from 3 to 6 of v of t dt, it's just going to be equal to the area of this triangle, which is going to be 1/2 times 3 times, you got to think for a minute, what's 3 times 6? 18. 18 minus 9 is 9. Boom. So we get 27 over 2. That's our answer there.
What is that? Is that 27 over 2?
27 over 2, yeah. Part A is relatively simple because they give us a left bound and a right bound. What makes this question more challenging is when you look at part B, they want us to write and evaluate a definite integral that represents the displacement from t equals 3 to any time t of x, and then find the exact same answer by using our new formula. So we'll practice that one more time. This is going to be very similar to what we did earlier with the area formulas. For part B, we're doing the area from 3 to x of v of t dt. Actually, I'll put the formula in there. It's 3t minus 9 dt. Now again, the only thing that's going to change here is that instead of 6 and instead of 9, we're going to have x, and we're going to have 3x minus 9 as our boundaries there. As long as 3 is left bound, this problem is pretty simple. If you move it anywhere, it gets a little more complicated. Yeah. Whoop. So this has the area of 1/2 times the base, which in this case, since now we don't know where that right endpoint is, we're going to have to measure it by calling it x minus 3 times the height, which again, we don't know where x is anymore, so we have to use the more general formula, 3x minus 9. And yeah, I know, if you got a good handle on antiderivatives, what we're shooting for is 3x squared minus 9x, 3 over 2. X squared minus 9x. That would do the trick. That's what this will all shake out to be if we've done it correct. We'll have the 1/2. Let's see, if we expand this, we'll get 3x squared minus 9x minus another 9x plus 27. So this ends up being 3 over 2x squared. Minus 9 becomes minus 18, but 18 divided by 2 is minus 9 anyway, so minus 9x. And you're also going to have this plus 27 over 2 thing going on there, which is interesting, but that's just the constant, because remember, this will it'll only be 3 over 2x squared minus 9x on its own if they're starting at 0. Anytime you move the left bound, all you're going to do is add a different constant on here. That doesn't affect the derivative at all. So this would be our kind of our area function. You might call it s of t, or s of x. And we wanted to evaluate s of 6. So I'm going to go to the calculator really quick and crunch this out. Let's see. I'm just going to make sure that it should end up being the same thing. It should be 27 over 2. I'm pretty sure it is. 3 over 2 times 6 squared minus 9 times 6 plus 27 over 2. Here, I'll show you. This is the part where I hope that I'm right. Hey, look at that. 27 over 2. See if we get the same answer no matter what. Now here is another question too. Is question C. This is setting the stage for kind of the next level of these kind of questions. But in question C, we're given what's called an initial condition. If you look at this first sentence, the millipede is standing on the 15 centimeter mark at t equals 3 seconds. That's what's known as an initial condition, because that 27 over 2 that we just found, what's 27 divided by 2? Hang on, I'm going to use decimals for this. 13.5, sorry. We got the same answer for parts A and B, which you'd expect because they're asking the same thing. But that's just how far the millipede has moved. That has nothing to do with where it currently is. That's just how much it's changed. In order to find out where it currently is, we need to know where it was at the beginning, and they kind of just told us. It was standing at 15 centimeters at t equals 3 when we started. So where will it be at t equals 6? What we need to do here is figure out, okay, it was at 15, and then we added on all this other stuff, the integral from 3 to 6 of v of t dt. And that's a little more of a complicated way to say it, but that's setting up for how we're going to look at these problems later on. You have your initial position plus the change. The difference is in question A and B, we're talking about what's called displacement. And displacement doesn't care about where you started. Displacement just cares how much it's changed. But in order to tell actual location of anything, you need to first know where it started, and then you're going to add on your displacement. So here we would do 15 plus 13.5 and call it 28.5. That's where the millipede currently is. So this is a preview question for a concept that we'll talk about later on, but it's a connection between displacement and location. And right now, I kind of want you to have some idea that you can find displacement by using an integral to accumulate your velocity function and work backwards. Because we're going to start moving away from area under the curve and start talking about accumulation, which has kind of been there the whole time. 55 is another really quick, just kind of one last little like, do you got the right idea here question. Tommy's trying to determine the integral from 2 to 3 of some function. He currently knows the integral from 0 to x is this function. So if he wants the integral from 2 to 3, here's a great way to do it. Just find the integral from 0 to 3 and subtract the integral from 0 to 2. I'm not going to calculate that with you right now. I'm just going to say that's the big idea. He doesn't have a formula for finding the integral from 2 to 3, but he does have a formula for finding the integral from 0 to x. So find the integral from 0 to 3, find the integral from 0 to 2, and subtract them, and you'll have the integral from 2 to 3. We don't need to actually calculate this because I'm not really worried about the calculation. Looking at all these problems here, I assigned all of them. I know, sorry. Sorry.
Yo, what?
I posted my answer guide earlier today. The one, I'll be honest with you, the ones I'm struggling with right now is B and C because my answers don't match the published answers, and I don't think they're right. I think I'm right. So I wouldn't be upset if you were like, I don't know how to do this. I'm like, I'm arguing with the CPM people myself. I think my answer's right. I forget what my answer was because I did it on my video and I wrote it down, but it's not what the book says it is. Yeah.
Will you read this?
Yeah. Okay, I'm going to stop this recording and